Okay, so I had a separate video to introduce amphoteric entities, and I gave you some extra homework questions. We're going to connect acid-base stuff to titration and pH curves now, so we're going to express all this graphically. You can do this as a little bit of a thought lab, and then I'm going to add on to it. But what I want you to do is sketch the pH curve of the continuous addition of a strong base, which is sodium hydroxide, right? The strongest base is OH negative, to a strong acid, right? So this is a strong acid, strong base titration. Label the equivalence point and the entities present in the solution before the equivalence point, okay? So I'm going to actually do this. So this is a Chem 20 review thing, right? You're going to label the entities at the equivalence point and after the equivalence point. We're going to choose appropriate indicators for the titration as well, okay? So this is the diagram that it will look like as you sketch along, but let's diagram it and let's see what this looks like. So this is a strong acid, strong base titration, and just a reminder, this is a review mostly from Chem 20, and it is HCl titrated with NaOH. So we start with a strong acid and we get increasingly basic. So we're going to start with a low pH. So if this is 1, there's 7 here, 14's up here. So we're going to start just kind of randomly at a low pH level. And then what happens with the titration is it hits equivalence. And strong acids and strong bases hit equivalence at 7, right? I'm going to talk about that like when we have, so what happens if we have a strong acid and a weak base, and a weak base and a strong acid. We'll talk about equivalences there as well. So just keep that in the back of your mind as we go. But my titration should look like this. Okay, and then this is my equivalence. So I hope this is jogging your memory a little bit. I'm going to separate the titration here. Now I have an area, so with each titration you have an area where pH doesn't change much, and that's called the buffering region. So you have a buffer area here. So here, so this is buffering, and then this is buffering as well. So it's where we're adding an acid or a base to the actual titration itself, but the pH is resisting being changed. Okay? So when we look at our graph, we have volume of NaOH added. And that's in milliliters. And so I'm also going to draw this, right? When we look at what's happening, you're going to have a burette and you're going to have an Erlenmeyer flask, and we're dropping the NaOH into the HCl. So this should all be like, familiar review for the majority of you. So the NaOH is being added, so it's the titrant, right? We're dropping the base into there, and then the HCl is the sample. Okay, so the HCl starts in the flask and the titrant starts in the burette. Now we've done lots of different varieties of titrations, but just as a reminder, right, the titrant, we know the concentration of it, but we don't know how much volume we need to add to the sample itself to neutralize the sample. So with the sample, we know the volume because we'll have stock sample volumes, generally 10 mils. Right, where we can do multiple trials. What we're trying to figure out is the concentration of the sample, right? So the titrant we know the concentration of, and the sample we don't know the concentration of. Okay? So when we look at this equation, right, we have HCl plus NaOH, and we're going to end up with a salt and a water. right? So that's your strong acid, strong base neutralization. Now, in reality, the HCl makes H3O+. Right, so when we know this from the last couple lectures of looking at the strong acids and strong bases. So here's my point 1, here's my point 2, here's my point 3, and here's my point 4. So what I want you to do is, let's identify the entities at each point. So again, this is review from Chem 20. So this would be before NaOH is added. And then this would be just before equivalence. And the sodium hydroxide, there'd be some of it. Okay, this is at equivalence. Okay, so I'm just going to write equiv, and then this is after equivalence. So when we, get rid of all the fluff with this equation, what we actually have is H3O plus OH negative. Right? And that's going to be a quantitative reaction that makes water. It's a strong acid and a strong base. Right? The Na plus itself doesn't participate in an acid-base equilibrium. It's a spectator ion. So when we look at what's in here, it's a strong acid. So I'm going to have H3O plus. Now remember, the HCl doesn't actually exist, right? The HCl dissociates and ionizes into hydronium, right? So I'm going to have Cl negative present, H3O plus, Cl negative, and there'll be water. So this will all be in an aqueous solution. Okay? So right before equivalence, what we have is, right, so as the sodium hydroxide is added and we start to neutralize the titration, we're going to have, what was there originally? You have hydronium. Okay, so there's some NaOH here. You have Na plus and H2O. Right, so the OH negative is the OH negative is reacting with the hydronium to make H2O. So there's no OH negative present here. Not yet, anyway. Okay, now at equivalence, there's no H3O plus and no OH negative because we're theoretically neutral now, right? So what we'll have here is the spectator ions and water. And as the titration continues, okay, we will start to add hydroxide. So we'll end up with a buffering region with a good chunk of OH negative, and that will resist the change in basicity. No. So as we keep going, there'll be a buildup of OH negative. You'll have Cl negative, Na plus, and H2O. Okay, so this is your point 1, point 2, point 3, and point 4. So just as a bit of a review there, okay, these areas are areas where pH is resisted. Okay? So that's, a quick review of some titration terminology. So let's go over what these different points mean. So the equivalence point, as a reminder, is theoretical, right? It's the volume and the pH in a titration reaction where stoichiometric equivalent amounts have been reached. So both reactants have been consumed and only products remain. So the reactants, right, would be the sample and the titrant. The proton transfer is complete, and theoretically there's no OH negative or H3O plus left over. We can't observe that though, right? That is an analytical value that we would need analytical chemistry equipment to do that. So that's your quantitative area, all right, in the titration. what we do see, we see the end result of the equivalence point as the end point. So if the equivalence is right at neutral, right, the end point is where we've gone past the equivalence, and there's now a little bit of the titrant left over. So the end point actually overshoots the equivalence point. So the end point is what we observe in a titration, and the difference between the two of those, as you remember, is the titration error. All right? So this is the value that we can observe. So this is my qualitative value, and this is what we really observe in high school chemistry. So the observed color change of the indicator or rapid change in pH, and we use it to estimate the equivalence point. So that's why we don't want to overshoot the equivalence point as much as we can avoid. That's why we do multiple trials, right? So we can decrease that titration error, right? So the difference, right? The end point is an indicator change. The equivalence point is actually a volume. Now, in an ideal world, they're identical with a small uncertainty of measurement. But the difference, there's always going to be more endpoint volume than equivalence, right? Because in order to get a permanent change in an indicator, you have to overshoot the actual neutral equivalence. So the difference between the two of those is the titration error, and that's what we try to minimize with multiple trials. All right? So we've got that, right? And then we have a buffering region in a titration curve, right? So it's the nearly level region of a pH curve where addition of a strong acid or strong base causes very little change. So the first part of the graph is flat, and then the buffering action ends at the equivalence. So once we hit equivalence, there's no more buffering, and then as we overshoot the equivalence point, we'll set up a reverse buffering system with the titrant now being the majority player in that concentration ratio. Okay? One thing that we do need to be able to do in these reactions is pick the right indicator. All right? Now, if I look in my data booklet, I'm going to have to pull this up here. So on page 10, all right, these are all of our acid-base indicators. With a strong acid and strong base, the equivalence is at 7. So what I need to do is pick an indicator that will change color close to 7. And you know, our common ones for strong acid, strong base titrations are bromophenol blue. So it shifts from yellow to blue just over 7, and phenolphthalein, colorless to pink. So once it starts to go basic, it goes pink. Now phenolphthalein, we generally use this one because it has a more, it's less accurate because of the pH range, but it has a more stark color change, right? So that's a big thing to keep in mind. So we're going to work on this, and we'll pick out the proper indicators for proper points in a titration. Okay. All right. So useful facts. So I've already explained some of this. So recall that neutralization is an acid and a base reaction where the pH is going to be neutral. So you make salt plus water. So the only time that we actually make a neutral final product is when we have strong acids and strong bases react. And I just showed that to you. So when you have hydronium and hydroxide reaction, so generally one substance can lessen the acidic or basic properties of another substance, but we don't necessarily neutralize. And that's because they're not necessarily dissociation equivalents. So if I look at hydroxide and hydronium on my acid-base chart, which is again on page 8 and 9 of my data booklet, hydroxide and hydronium completely cancel each other out. But if we look at Ka and Kb strengths, right, so Ka and Kb, the stronger the Ka means the stronger acidic component, right, whereas the weaker the Ka, meaning the weaker the acidic component and the stronger the basic component, right, and we can solve for Kb with the Kw relationship. You don't generally get neutralizing factors, right? So If I have oxalic acid that reacts with HSO3 negative, for example, the oxalic acid has a pretty strong Ka value, and this has a very weak Kb value, right? So this would be a very, very weak base, and that would be a relatively strong acid. Okay, so they're not going to neutralize each other completely. So if I have a strong acid and a weak base, you'll have a different pH equivalence point, which we'll talk about as the lecture goes. All right, so the pH curve itself shows equivalence, and it helps you select the best indicator. So where we have equivalence is at different levels of pH is where we'll pick the right indicator. The endpoint itself is the indicator color change, and it's the addition when we stop adding the titrant, right? When you graph, we already talked about equivalence, so it's a quantitative value that we find through stoichiometry. When we post these on a graph, so when you look at an acid-base chart, the endpoint itself, we find, so the endpoint is a pH value, okay? That's going to be on your y-axis, so my endpoint will be indicated on my y, and then my equivalence point will be the volume of the titrant added, and my equivalence is on the x-axis. And the two of those combined gives me my neutralization point. Okay, so I'm going to leave that there for a second, and I'm going to give you some examples of how we would indicate different points of buffering or points of equivalence on a graph. Okay, so let's look at this. So this is example 2. 25 milliliters of 0.48 mole per liter NaOH. Let's say it's titrated. So that means this is the sample, because this is the thing that's being titrated. All right, it's not the titrant itself. So it's titrated with 0.50 mole per liter HCl. There's my title. The title tells you what's going on. So this is the titrant, because it's the one doing the titration. So if I look at this graph here, pH, and then this is volume of HCl added. So the HCl in this case would be in the burette, and the NaOH would be in the Erlenmeyer flask. Okay, so I have NaOH and HCl. So this is strong acid, strong base. And the NaOH is what's in the flask. So we're actually looking at the pH change of what's in the flask. So this starts as a base, right? And my curve is going to look like this. And when I look at what is what, this is my endpoint value, and then this would be my equivalence. All right, so the x-intercept is my equivalence, and I can measure how much that would be in milliliters. And this, let's say this is about 25 milliliters. It's a little below it. So 25. All right, so this would be whatever value this would be about 24 mils. If I were to measure all this out, and then my endpoint is 7. So the endpoint is a pH value, and the equivalence is a volume. Okay, so we're going to start. Let's take a look at this graph. We start with all NaOH in the flask, and then down here would be all HCl. And let's look at what's happening at these different points. So 1, 2, 3, and then we'll look here at 4. Okay. So if I kind of give you a little bit of a word explanation as to what's going on here. We have a large amount of OH negative and H2O. So any HCl added is immediately converted to water. And we've talked about this, it's just called the leveling effect. Right, so water, because of its polarity, it does a really good job at neutralizing strong acids and strong bases. Eventually, that polarity with the hydrogen bonding will be overcome as we add more HCl and we continually make more H3O+. Okay, so I'm doing the same thing here as I did over here identifying the entities. I'm just describing what's going on instead. So if I have NaOH here, you know that there's going to be Na plus present and H2O and OH negative, and that's all there is there. Okay? So we're at 2, we're about to hit the equivalent. So there's about to be a big change. That's what's happening at 2. So there's OH negative solution. Nearly completely consumed. But we're able to buffer here. So this is a buffering region. So we've been able to buffer up into this point. So buffering region present. pH is relatively unchanged as a result. So if I were to look at what's present here, there would be Na plus, there would be Cl negative because we've been adding HCl. There would be H2O, and there would be OH negative, and then a little H3O plus. Okay. 3, that's equivalence. So what would be present here? So there's no OH negative and no H3O plus. So they've both been neutralized. Okay, so what is present here is Na plus, Cl negative, and H2O. Okay. 4 is after equivalence. Okay. And this is excess acid. Added, so there might be a little OH negative. But solution has, okay, and I'm going to put that as maybe. There might be because of ionization. But the solution has primarily H3O plus, H2O, and spectator ions. Okay, and then pH remains stable. And as H3O plus is added, another buffering region is created. Okay, so I'm going to have a buffering spot here. So we'll start to resist pH change as well. All right, so but it's created in a reverse fashion, right? So we'll resist the change from 7 to a very low pH here. Okay? Let me give you, let's look at this one again. Actually, I'm not going to draw the graph again. Let's take a look here, and here, and here. All right, so this is buffer region number 1. That's equivalence. And this is buffer region number 2. Okay, so let's say the question asks you, how could you determine that we have hit buffer region number 1, equivalence point, or buffer region number 2 in the titration? All right, so how do we know we are in buffer region number 1, equivalence, or buffer region number 2? Okay, now we have no way to know this quantitatively. What we will be able to determine is this qualitatively. So we'll need a qualitative observation. And that's an indicator, so we need to add the right indicator. Okay, now on the graph, this is about a pH of 12. Kind of skimped on the graph here, but. And then this is a pH of about 2. So what I need to do is, when I've been able to indicate where the buffer regions are on the graph, I need to be able to add appropriate indicators into my solution. And they'll change color as the titration goes. So when we hit the buffer region, I'll get a color of an indicator. And when I hit this next equivalence, the indicator color will change. And then when I hit this next equivalence, when I hit this buffer region, I need an indicator that'll change color as well. Okay? So I'm going to pick an indicator that changes color at a pH of about 12. So as the pH drops, all right, we can look at alizarin yellow. Okay. So it will turn, so anything above 12 and it's red. Once it hits 12 and below, right, so you can see 10.1 to 12, it'll be yellow. All right, so as it gets under 12, the indicator goes from red to yellow. So I'm going to add that in here. So the indicator that I would add into my solution to know when I hit buffer region number 1 would be alizarin yellow. So I'm picking different regions of my acid-base chart that I'm going to have equivalent indicators for. This at equivalence, so that's region number 2. It neutralizes at 7, so I'm going to use bromothymol blue. You've already talked about this, right? Or phenol, PHTH, phenolphthalein. And then 3, I want to pick an indicator that's going to change color at a low pH. So if I look at orange 4, once we get sort of below 2, it goes from yellow to red again. So my solution should start, where's my alizarin yellow? It should start red, turn yellow, all right? And then I should get a blue tinge from using the bromothymol blue, or a pink color from using the phenolphthalein. And then these go neutral. And then when I add my orange 4, the solution should finish red again. All right? So it'll change color here. So that is orange 4. All right, so from my titration curves, I need to be able to pick out these different regions. I need to be able to identify entities I need to be able to use appropriate indicators for different parts of the titration progress. Okay. Are we looking for time on that? 20 minutes? Perfect. Okay, so indicators, just so you know, indicators are substances that change color when reacted with an acid or a base. So here's what indicators are. Indicators are actually conjugate weak acid base pairs. So they actually change color because of equilibrium shifts. All right, so if you look at indium here, when indium is bonded to hydrogen, okay, so when it's in acidic solution, it's colorless. All right, and then all right, so, and then, in acidic solution here, it's pink with the hydronium present, all right? And in a basic solution, it is colorless, all right? So indicators work based on Le Chatelier's principle. So if H3O plus is added, all right, you can see here the system shifts left, and you get color number 1, okay? So H3O plus added, we move over here and we get color number 1. So the HIN will be colorless when we add acid. If OH negative is added, in this case, the hydronium will be consumed and will make water. So that's going to be seen as a deficit of the hydronium. So if a base is added, then the equilibrium system shifts to the right and we get ion negative. Okay, and then you get the color pink. So pink represents a basic solution. All right, so I think I messed that up for a second there. So colorless in this case means acidic because of the shift away from the hydronium because of equilibrium. And then the OH negative is indicated, so if we add OH negative or a base, it's indicated as pink because the H3O plus is removed from the equilibrium. All right. So if an indicator is an acid, increase H3O plus will shift reaction towards the acid indicator side, right, the weak side of the acid-base reaction. And if the indicator is a base, the OH negative will shift the reaction towards the base indicator side. All right? And here's the deal, right? Different indicators shift at different pHs due to their Kas. Okay, so you have some questions. Page 754, numbers 1 through 4, looking at that. So you can add that to your homework list. Okay, but acids and bases act and react based on Le Chatelier's shifts.